So previously, we developed the exponential function derivative using first principles, and we end up getting this. So the derivative of an exponential function is pretty much itself. However, there is going to be a value in front depending on what the b value is. So if we wanted to find the derivative of 2x, we would know that the derivative is also itself. However, we have to figure that number in front by substituting the b for here and using your calculator to figure out the value when h is very, very small. And we end up getting 0.693, some sort of vertical compression factor on the 2x. Now, in the previous video, we discovered the value for e. E is a special number, 2.718, and when you determine the derivative of 2.718 to the power x, it is pretty much itself. So for this question here, the derivative is going to be also itself. However, we know that this is a composite function where there is a linear within the exponential function. So we have to take the derivative of also the inner function. In this case, is going to be 2 using the power. So here we're going to recap before we develop the derivative of an exponential function in a different way, not using first principles. So going back, the last log law we did was this. So when you have a composite type expression where you have a log within a bigger picture exponential function, notice the bases are the same. The base of the exponential is the same thing as the base of the log. Over here, we're going to bring the n inside using the power law. And if you notice, the bases are the same, and that results in a simplified version, which is m to the n. So in this next step, all I did was change all the bases to e. And we end up getting the same results. Over here, the only difference is log base e can be expressed as ln, a different format. So in this next step here, I just rearrange. I put from left to right, from right to left. Okay. So our interest right now is not m to the n. It is exponential form, but we're actually interested in b to the x. So instead of m to the n, I want b to the x. So everything here is pretty much the same format, but I'm just expressing everything in terms of b and x. So in this step here, we have 4 equivalent expressions. They're all equivalent, they just look different. So if I can find the derivative of this piece, I'm pretty much finding the derivative of b to the x. So I'm going to take these two and rewrite this out. So over here, let's find the derivative of bx, but we can't do that directly without using first principles. So what we're going to do next is let's actually rewrite the equivalent of b to x, which in this case is ex log eb. Okay. Now I'm going to sort of reformat this. I don't want so this piece here is actually a constant. B is the base. We know that base is going to be some number that's greater than 0 but not 1. E is 2.78. So this is actually a constant. So I'm going to call this k. So now we have e to the xk, just to make it look more simple for now. Okay. Next step is I'm just going to switch around the k and the x because we're used to having constants in front of the x value. So let's actually take the derivative of this, which we can because we did in the previous slide. We did e2x. So now it's ekx, which is pretty much the same thing. So we know that the derivative of this is itself, e to the kx, but we know that there is it is a composite function where there is a linear function kx. So we have to take the derivative of kx, which is just a k. So let's rearrange this, k e kx. And we're going to bring back the k afterwards. So the k is going to be this thing over here, log e b e log e b to the x. So if you notice this piece here, this piece we can rewrite it as log base e is the same thing as ln b. Now this piece here, if you can go back to this part here, it looks exactly the same thing as this piece here, which is the same thing as this piece here, which is the same thing as the exponential function. In other words, this is going to be b to the x. So using the log laws and e to the x derivative, we actually derive the derivative of bx, which is ln b times b to the x. So this one here was from first principles. This was from log laws and derivative of exponential with base e. So if you notice here, they both have bx, that's the thing they have in common, but what's interesting is that this thing here actually will determine that, I'll call it the compression or stretch factor. So for example, let's go back to 2 to the x. So y is equals to 2 to the x. When we did the long way using the calculator, we get 0.693 times 2 to the x. Now, if we use this method here, all right, the derivative is going to be 2 to the x, and then the number in front is going to be ln 2. Now, if you type in ln 2 in your calculator, you will get 0.693. So what that means is, I have enough space here, that ln b is the same thing as the limit over h. So let's now take the derivative, or find the derivative of another type of exponential function. Instead of 2 to the x, let's do 6 to the x. So f prime is going to be, there's going to be two pieces. Well, the first piece is, we know the derivative of exponential is pretty much itself. However, there's going to be some sort of stretch or compression factor. In this case, that number is going to be ln 6. We no longer have to use this limit and substitute using our calculators to get this number. If you type in ln 6, you'll get a decimal place, but you can just leave your answer as is. Now this one over here, g of x, looks very similar to this one, but now we have a 2x. This here is a composite function. There is a linear, or mx, or 2x within the 6 exponential function base 6. So in this case, the derivative is going to be two things. We need to find the derivative of the bigger picture, which is it is itself. Just copy down itself. And then you have to find the compression factor or the stretch factor, which is ln 6. So that's the first part. This is the outer function, the bigger picture. The next thing is you need to figure out the inner function, which is 2x. In this case, using the power rule, is going to be 2. And then you're done. So we'll do two more examples. Keep it simple. What happens if you have hx equals to, for example, ex squared? What happens if the base is 2.186? Well, you can actually do the same thing here. So this is a composite function. There's a parabola, a quadratic function within the exponential function. So the derivative of this is the bigger picture. It is itself. Now, you want the stretch factor or the compression factor, you can actually write down ln e. However, ln e is the same thing as 1, meaning with the special base of natural numbers, there is no stretch factor. So you can just leave it as a 1. You don't need to put ln e. However, don't forget, we dealt with the bigger picture. Now we got to deal with the quadratic. In this case, it's going to be 2x using the power rule. So the last example is actually a general example. What happens if you have an exponential function, but then you have a function within that function? So this is a composite function. So to do the derivative of this, general statement is, okay, well, bigger picture is exponential. We know that exponential has a stretch factor or whatever compression factor, ln b. That's your first piece. The next piece is the exponential function is itself, f of x. You leave the inner as is. And then the last thing you're going to do is find the derivative of the inner function. In this case, it's going to be f prime of x. So I think right now is a good time for you guys to go to Google Class and go to the links. And there are some videos that are created by, I think, University of Waterloo for you to look at. They actually go through derivatives of exponential functions using the different types of rules, quotient, chain, and product.